3-1 to 3-2. What was 3-1? Because critical numbers was 3-2. What was 3-1? Absolute extrema, absolute highest, absolute lowest, looking at graphs. But also, wait a minute, guys, critical numbers.
No, we didn't write this down. No.
Critical numbers were first talked about in section 3.1, right? So the forever card on critical numbers, who are they? Well, critical numbers, there are the zeros and the d and e's of the first derivative, and that's what's seen by, you're welcome, Adam, the pitchfork. But the pitchfork, the zeros and the d and e's. Now, the pitchfork is only good for what kinds of derivatives? The derivatives that have division, right? Numerators and denominators, or end up being quotients. But we still think about zeros and d and e's even for non-fractions, just the pitchfork is a helpful reminder for fractions. But Kyle, why did you say, wait a minute, this wasn't 3.1. I think you were the one that first said 3.2.
Yeah.
What's 3.2? What's going on in 3.2?
3.2, we started to talk about the mean value theorem.
3.2, we were talking about MVT, mean value theorem, and technically roles, but it's kind of like in MVT, right? We're talking about roles in MVT. And in roles in MVT, wait a minute, did we talk about increasing, decreasing at all in section 3.2? Or was it just MVT and roles?
Just MVT.
Okay. So 3.1 talked about what critical numbers are, talked about extrema, the difference between absolute and relative. And we talked about anything else? Absolute, relative. Oh, EVT, extreme value theorem, and how to find absolute extrema. That was section 3.1, making little baby tables and plugging in, finding out what critical numbers are for the first time. 3.2 said MVT. There's this whole idea about average rates and instantaneous rates and secant lines and tangent lines, and how did those all go together? Wait, on the last test, did you guys have your very first long answer be a tangent line? That's like a really key concept in calculus. So even though I'm saying you don't have to have that whole test mastered, should you know how to find a tangent line? Yeah, and a lot of you guys rock that problem. Like if you studied for that test, for the most part, maybe you missed a couple points here and there with a bad derivative or something, or you forgot the whole normal perpendicular thing. But most of you rock that tangent line problem. Good, key, fundamental concept. Okay, so tangent lines and secant lines, average rates and instantaneous rates, that was MVT. Section 3.3 is where this actually was, not 3.2. Section 3.3. What's the title to section 3.3?
Increasing,
decreasing, and the first derivative test. You guys in your head even know the title of that section. How do we talk about, or what do we need to look at for increasing and decreasing? First derivative, right? So, what's section 3.4? Concavity, another behavior we're going to analyze for, and which derivative test? So what do we need for the concavity? Second derivative. What do we need for increasing, decreasing? First derivative. Okay, so did we have a forever card for when something is increasing or when something is decreasing? Something meaning box, maybe sometimes an F, maybe sometimes something else. When box prime is, well, let me ask it this way. When does box increase? Oh, you silly guys. It's when you look at Box's graph and he's going up. Well, that's one way, but that's the easy pre-cal. You're looking at a graph and it's going up way. What's most of homework? You guys were just looking at homework number 19, right? Is most of homework, let's look at a graph and say it's going up or going down? So, one more time. You guys were right. I was just being facetious. When is box increasing?
When box prime.
So let's look at box prime and let's see where he's positive. But wait a minute, can we just look at box prime formula and be like, oh, I magically know it's decreasing? Wrong word. It's negative here and it's positive there and it's negative there and it's positive. No. Those get super complicated. So instead, we need to make like an actual break down its domain, make some sort of sectioning, make some sort of intervals to say, you know what? Whatever he's doing it this whole time, and that whole time, and this whole time, and that whole time. But we have to break up that number line with the special points, x values, where it could change how it behaves. It meaning the original function. So its derivative could change signs. And how can a derivative change signs? How can a derivative go from negative to positive or positive to negative? What must be happening in between sign changes? Maybe, but not necessarily. Just think the numbers. If I'm going from positives to negatives or negatives to positives, I, what do you have to cross in between? 0. If the function is continuous. If the function is continuous, the only way to get from below the x-axis to above the x-axis is to hit a 0, right? We had a graph of a derivative yesterday. And the only way to go from below to above were those x-intercepts. Or to go from above to below is an x-intercept. Now I said if the function is continuous. Because if it's not continuous, couldn't it be above 1 second like this and then have a vertical asymptote and then be below? You can jump if there's like a hole. You can jump if there's a vertical asymptote. You can, So can we just look at zeros? No. For continuous functions, it must change at zeros. But for discontinuous derivatives, I also have to look at, that's silly. I already know this. Critical numbers are either zeros or DNEs. Now, why am I spending so much time on critical numbers, homework number 19, increasing, decrease, homework number 19, and talking about those little sign charts, homework number 19, when we're supposed to be talking about 3.4? Could I be vamping us up for our questions that we're going to be doing on section 3.3, homework number 19? Yeah. Could I also be drawing comparisons to what we're going to be doing in 3.4 for concavity? Yes. Because you guys without me, talked about the first derivative test on Friday. And the first derivative test says, hey, once we know this whole increasing, decreasing behavior, remember, analyzing behavior of f, we need to look at the f prime to help us out. Because we have those critical numbers that can section it up into intervals, and then we can just test one little baby point and see the positives or negatives of the derivative. If we can analyze the behavior of f from f prime, man, we're doing pretty good. The only problem is, guys, in this analysis, using the first derivative, do you see any curvature? No. All we know is up and all we know is down. We don't know how it's going up. In an increasing way, where the rates are increasing, slopes are increasing, or in a decreasing way. You can go up like an ln, or you can go up like an e. Very different going ups, right? So first derivative just tells us going up. We need critical numbers, we need some derivative skills, we need to make some sign charts. This is homework number 19 that we're going to go look at right now. You could not tell curvature. Now you're looking at graphs and you're like, they have curvature. You can't tell curvature, but you can tell that whole increasing, decreasing thing. Some of you guys might have used tables, but hopefully simpler than the books. Some of you guys might have used number lines, hopefully accurately and carefully. Let's go ahead and talk about homework number 19 real fast. And then, with all of that review, let's see how section 3.4 is so similar. Here we go. Homework number 19. Did you guys have any questions on the derivatives? On Friday, you were supposed to have your derivatives done and simplified. I had the answer key on mine. Are there any ones you're like, I don't know how this jump happened? Kathleen? Number 11. Why is number 11? Look, in a way, not too bad until you start taking its derivative. What rule do you need?
Chain.
Yeah, you do need chain rule because there's a square root and there's an x squared. But even beyond chain rule, you also, or bigger than that, you have a product, right? So you have product rule and chain rule. And I know some of you are like, nah, whatever, derivatives, I got it. But guys, as we can all tell on that test that I just gave you back, do we all tend to make mistakes on derivatives? Yes or no? Yes. Now, I'm not saying that you don't know your rules. Some of you don't. I'm not saying that you can't get it. I'm just saying it's easy to make mistakes. So, Kathleen, I'm going to go really fast because I'm guessing that you tried it and you just got stuck somewhere, okay? So, second D first, pretty basic. First D second, it's a bit rougher because I have to think about this as a 1/2 power, right? So then bring down my 1/2. Negative 1/2 is going to pop that dude in the denominator. But, as John, that was you, right? Chain rule?
No, that was
Kyle said chain rule. I have to
I said product.
Wyatt.
I said product.
Okay, hey, we'll put you two together and we're good. So, it's called collaboration. That's why we work in teams. Negative 2x. Right? You bet. Now, the dilemma is, I believe, for most of this homework, you had to get critical numbers. Didn't you guys just see a pitchfork? Pitchforks were for when we had fractions. Do we have a fraction?
Almost.
Yes. But what's the problem? This guy's an over 1. We have a... what do I want? 1/2. one nice put together numerator, one nice put together denominator. The only way to put together fractions is to get a
common
denominator. Oh, it's going back to basics. So, common denominator. I'm looking at this really quickly, Kathleen, and seeing if anything simplifies, like the 2's, which makes life a lot nicer. A little bit nicer. And see that this dude's missing that dude's denominator, so I have to multiply. And maybe if you're looking, you're like, oh, I think that's going to be nice. Because a square root squared ends up just being the original function, right? Square root squared will simplify. 16 minus x squared plus, and then I have, a negative x squared. I do believe. Double check my math with what you guys got.
Yeah.
So I see a 16 minus 2x squared, which is the same thing as 2 times 8 minus x squared. If I'm looking for zeros, well, right here I see x can't equal DNEs, right? Positive and negative 4, but if you notice, that's just our natural domain anyway. So those aren't really critical numbers. They're more like endpoints. And then up here in the original, I have 8 minus x squared equals 0, side subtraction 8 divided negative. I have plus or minus square root of 8, which is plus or minus simplifying 2 root 2. Those are my zeros, right? Now, help me out, Kathleen, real quick. What were the directions for number 11? It's not just critical numbers, right? Are you analyzing? Oh, just kidding. Just critical numbers.
Oh, for the whole problem?
But you kept going?
Because that's just the derivatives. That's not the whole homework.
No, I know. I was asking derivative questions. I'm guessing you had a question later on.
Because I couldn't find the derivative, so I didn't do the actual problem.
Oh, got it. But does the derivative make sense now? Yeah. So the tricky thing is whenever you have a square root, almost always it's like, it's not a fraction. Just kidding. Yes, it is. Oh. And then you have to probably, with a product rule especially, get common denominators and then go for your zeros and your d's. Okay? Are there any other derivative questions? Okay, now once again, you don't have to be a master at the last test, those kinds of derivatives, but you do need to be able to have the basics now. Okay? Product rule, chain rule, quotient rule, fractions, get a common denominator, get those derivatives simplified, right? Trig and ease, I know they get nasty, you're not going to have a lot of them on the test on Friday, maybe a couple. But you need to know your rules, derivative L and the view, E to the etc. Now, I'm going to keep on scrolling to actual homework 19. So let's just assume we have the derivatives and we have them right, aka let's assume we have the critical numbers. Did you know how to use them? Now, I showed you yesterday. Did you have to make a table like this? No. Why not just put a little like f prime is negative, f prime is positive, save time. Put a little down arrow. Remember, f prime doesn't tell us curvature, just says down. Okay, whatever, you're decreasing. Or whatever, you're increasing. Don't know the curvature, I don't know how, but I do know you're going up. Do you guys have any questions that we need to revisit on how to make the tables, how to do the analysis for the rest of them? Anything on homework 19? Sure. Okay, I don't mind moving on because then we get to cover homework number 20 a little bit better. Last night in homework number 20, I do believe, I think I put a comment. You guys get advised when I put comments on things, right? In Google Classroom, like little emails or something? Yeah. Okay. So I went ahead and advised you guys that I had put the answer key to homework number 20, and I did a quick little like, hey, these are the ones you definitely want the second derivatives for. Were there any of these for those of you that did derive? Hey, I like this guy. He was nice, right? Wait a minute. Oh. Now, I didn't tell you you had to keep going, but do you see how they set the second derivative equal to 0? Or do you see how they... Oh, that's interesting. They're talking about the function not being continuous. We talked about that so far. Hey, look, they're setting the second derivative equal to 0. Second derivative equal to 0. Second derivative equal to 0. I think they're doing zeros of the second derivative for section 3.4. It's like the zeros of the first derivative for section 3.3. But do you guys have any questions on derivatives so far of the ones that you've tried, if you tried? Kathleen? 19. Anything else besides 19? I see your trend, kiddo. Which ones don't you like? But hold on. Can the rest of you benefit from this and be like, oh yeah, it's tricky, it's hard? Yeah. Right? Okay. Sorry, any other derivatives that we didn't like last night? Okay. So, the chain rule?
Yes. Only.
Let's go.
Good.
Well, but you should think about it, right? Okay. But nice. Second. D first. It's easy. Plus first. D second. Can I just put the square root under there?
Yeah.
Why did Wyatt say? Because I said, do you need the chain rule? And he was like, yes. What's U prime?
1.
So would you have gotten messed up if you had forgotten the chain rule? No, but you should still always think about it. Why am I putting that over 1? Can't you just go take a derivative again right now? Yes. But if you were listening carefully in class yesterday, I advised you to get to a fraction as soon as possible and then do quotient. So let's just say you were looking for critical numbers, and if you were looking for critical numbers, wouldn't you want this to be one nice big old fraction? And Kathleen, sorry, this one, the 2 does not reduce. So I'm kind of stuck with that 2 being a part of that common denominator. So I have to multiply this guy by 2 square root to get that common denominator, but still a square root squared is going to be x plus 3 times 2 is what this becomes. That's going to be 2x plus 6 plus 1x, so 3x plus 6. Now, if I could simplify something, I totally would, but I don't see much being able to be simplified.
No point out of 3.
Yeah, not really, right? But question, why am I making way more space? What's the objective in homework number 20, section 3.4, concavity? So I need the second derivative, which means I need to go again. No! Yeah, sorry. So the second derivative. Quotient rule, yeah, guys? So bottom. D top. 3, right? Minus top with parentheses, don't kill that seal. D bottom. I have to bring down a 1/2 and then. Why should I think of the chain rule? Yes. But just 1. All over. No, it's a fraction and a fraction. It's okay. Complex fractions. I've been telling you since the beginning they were important. Before the beginning, it was a fun. Anyway.
Wow.
Whoa, whoa, whoa. I thought you were supposed to do bottom squared. Oh, 2 times 2 is 4, and a square root squared is. Kathleen, there are 2's. That's nice. But, dilemma. Don't I now have, hold on, sectioning off, we have that, and then we have minus, and then we have that. Don't we have a little guy we have to deal with, right? What do I do with complex fractions if you're doing my way? Multiply top and bottom by that little stuck dude, right? And he needs to go to this piece and to this piece. Now, in this piece, life is good because he just goes away and I get my minus 3x minus 6. Ooh, that negative has to distribute. But over here, actually, wait, this isn't bad either because it's a square root squared. So 3 times 2 is 6.
6 times x plus 3.
Oh, I have an equals and I have lots of room. 6 times x plus 3. I don't know why I have all that room. All over. Oh, gross. I have that and that and that. Yeah, but isn't this a 1 and this is technically a 1/2? So couldn't I just write it as 4x plus 3 to the 1 1/2? Or 3/2? What? And then I have 6x minus 3x is 3x. I have 18 minus 6, which is 12. I think I can do some factoring out there, kiddo. Is this looking pretty good?
Wow, that's a lot of work.
It's a little intense, but pause. It's a derivative with a product rule. Square root is a 1/2 power and a quotient. Complex fractions. Algebra, calculus coming together. All for the purpose of setting equal to 0 in D&E. Why are we setting the second derivative equal to 0 in D&E? Well, no one else asked any other questions. So let's get back to notes and remind ourselves of why we're taking the zeros or D&E in session. That's an assignment that we're seeing. 3.4. 3.4 says it's great to know something's going up or going down, but now we need to talk about curvature. Now, does everything have curvature? No, absolute value functions. They're just straight lines. Think about your basic graphs, guys. How many of them have curves? Most. Right? Yeah, probably even more than 75%. Who has a line? Absolute value and lines. And greatest integer. The first four, well, not the first four, but the top four on mine all have lines, and the rest of them have curves. So how many functions have curves? Almost all of them. So for analyzing the behavior of functions, it was great to know the going up, going down. Now we have to talk about the curve. But, question, couldn't I, for what I wrote yesterday, couldn't I say things like, for this one, if I was to split up at the horizontal tangent, for this concave up, I have f prime being negative, decreasing, and then f prime being positive, increasing. But what's f double prime for all the concave up? Positive. I can know he's going down. I can know he's going up, but I don't know the curvature unless I know him. Just check it. This guy's decreasing. This guy's increasing. AKA the derivative is negative. The derivative is positive. But isn't this guy also concave down? Isn't this guy also increasing? No, you can increase this way or that way. Mm-hmm. Do they look the same? So if I know increasing from the first derivative being positive, I won't know the curvature unless I look at the second derivative. For this one, I have him increasing to the horizontal tangent and decreasing after, but he's concave down the whole time. Concave down can be just increasing. Concave down can be just decreasing. I need to know the sign of the second derivative. So what we talked about yesterday was favorite card number 25. We're halfway there. I'll give a shout out. How do we know concavity? How do we know concavity? Concavity for a given function, curvature, is determined by the sign of the second derivative. Concavity, curvature, is determined by the sign of the second derivative, which makes sense though, because as we looked at concavity and curvature yesterday, we saw if f prime is increasing, then that curvature is always up. If the slopes are getting steep, and positive slopes are getting steeper. If the numbers are getting higher, more positive for the slopes, my curvature is up. Which, if f prime is increasing, that's increasing, decreasing test. If box is increasing, then box prime is positive. I know, I just covered up the prime. Kind of defeated the purpose. Hold on. If box is increasing, then box prime is positive. So technically, you could also think about this as the slopes increasing or decreasing. The graph of the derivative increasing or decreasing will tell me about box prime sign, which will tell me about the curvature of the original. Uh-oh, there's more that we could have known from the graphs of those derivatives yesterday. And then for this last number 3, I told you to take out this whole f prime is constant and just say if f double prime is 0, there's no concavity of f there. Let's just leave it there. There's no concavity of f at that point. So we don't really know. Maybe it's a possible inflection point. So, whoa! What does this look exactly like?
3.3.
See why I started off class with 3.3? Does much change for analyzing for concavity? No. So you write down what you need. You write down what you need. It's the exact same process. All that's different is who are we looking for this time? The second derivative. Are we still thinking about domain? Yes. We're still thinking about the domain of f. We're still thinking about continuities of f, the continuousness. We're still thinking about domain. We're still going to do check domain problems, but we're not reviewing it this time because we talked about it in section 3.3. We're solving for homework number 20A, that was optional, solving for derivatives and second derivatives, getting the second derivative simplified to find the, wait, you didn't call them critical numbers. Pips. Sure looks like a acronym for something. P period I period P period apostrophe S. Who are pips? Possible inflection points.
Alright.
Because didn't I show a over here? But hold on, wait. Over there it said if f double prime equals 0, no concavity is a possible inflection point. You're showing a pitchfork, and a pitchfork says we should look at the zeros and the. I didn't give you all the cases on the last card. Second derivative could also not exist, just like critical numbers. The first derivative could not exist, and we still have to check those. But guys, then check it. All we do is a sign chart. In a sign chart, we just don't use critical numbers. First derivative zeros, DNEs. We use pips. Second derivative zeros, DNEs. On a number line or in a table, plugging in a test point, checking a sign, and then sketching a conclusion. So basically the exact same thing, but with basically the exact same thing, but with f double prime. Now, we're going to analyze somebody for concavity. Whoa! But he's an easy guy. I know. Don't we normally start with easy guys?
Yes. Most of them.
Okay. I'm going to analyze this guy for concavity. And we're doing an easy guy. Just for sake of time. Because my job is not to teach you derivatives in these chapters, or in these sections. Your job is not to be a master of derivatives. Wait a minute. Why am I simplifying the first derivative? Don't I want to get to the second derivative? Second derivative simplified. Found the first derivative, double check me, but I think I'm good. Found the second derivative, double check me, but I think I'm good. All for the purpose of finding my possible inflection points of my original function. Technically possible critical numbers of my derivative. You want to think about it. But my pips are going to be, can't be DNE, so forget that, but it can be 0 at 0 or 2/3. Both of those are within my natural domain of all real numbers for this polynomial function. And I'm going to make myself a sign chart. In my sign chart, I'm going to mark my 0. I'm going to mark my 2/3. And we're analyzing this time for f double prime's sign. All to try to figure out the behavior of technically f, but an added bonus is we're also going to know the behavior of f prime. Because as we check the sign of f double prime, we will know the concavity, the curvature of f, and we will know the increasing, decreasing of f prime. It all comes together.
Burrito.
Now, if I was to test the sign of f prime, also, technically, I guess we could know the increasing, decreasing of f2, but we're not going to put all of it together until after Thanksgiving break as far as here's a function and let's do everything possible from all the training you've ever received in math up until now to graph them. That's after Thanksgiving break. So, you guys know what to do. You retest, right? But this time, instead of testing, I don't know, -1 in the first derivative, where are we putting them? So your brain is going to definitely be helped by you remembering which guy you're going to, right? So, -1 plugging in, ew, I don't know. Oh, here, easier. Negative times -1, -3 minus 2 is negative. A negative times a negative is a positive. Plugging carefully. 1/2 is in between 0 and 2/3, so 1/2 would be whatever, positive. 1/2, 3/2 minus 2, that's a negative. 1.5 minus 2. Okay, positive times a negative is a negative. And then, I don't know, plug in 100. Positive and positive. What does it tell me? Concavity concavity of f is up. Now, wait a minute. Do I know if it's this up or that up or that up? No. I just know. So I'm going to make it just quick and brief. I just know concave up somehow. We'd have to put all of our analyses together to figure out exactly which type of concavity. This next one concave down somehow. This next one concave up somehow. The sign of f prime, double prime, sorry, shows me the concavity of f. But an added bonus, it shows me that f prime's graph would be going up here, and it would be going down here, it would be going up here. Well, that's weird. F prime has a leveling off, it seems, at 0. Oh, because the second derivative is 0, which is a critical number of the first. Anyway. So long story short, could I say that f is concave up from negative infinity to 0 and 2/3 to infinity? And concave down from 0 to 2/3? Why, yes, indeed I can. And if you guys look at, you don't have to sketch this graph. I'm just showing if you had a graph. Do you see that concave up curvature? From negative infinity to 0? And then concave down curvature to what? It goes concave down just for a little bit and then concave up for the rest?
Whoa.
Concave up, concave down, concave up. Now, I see this guy. This guy's a relative min. Oh, wait, that's weird. It's concave up before that and concave up after it. The min is just kind of in the midst of it for my f. Who's this guy again? That's a min. Who's that guy? Oh, and who's this guy? What's so special about 0 and 2/3?
Well, they're crits.
They're crits of the first derivative if I was to graph him. They're pips of the original. Are these actual inflection points? Not just possible, but actual? Does the curvature change?
Yes.
Yeah, like a tangent curve or like a cubic curve. And does the curvature change? Yes. What does it take to have an actual inflection point versus a possible inflection point? Well, I've been talking about it for a couple of days now. Points of inflection. Well, I talked about it right now. Sorry for something. Point at which concavity changes. How can they occur? Well, maybe it's like a tangent. Maybe it's like a sine or cosine. Maybe it's something else kind of weird like you guys just saw. Or there could be a couple different ones. Somehow before and after the curvature changes from a downish, frownish to an uppish, smilish. Possible inflection points. Like critical numbers, f has to exist. But unlike critical numbers, we're looking at the second derivative being 0 or dne. Those are just possible inflection points. What does it take to be an actual inflection point? The sign of f double prime has to change. Now the nice thing is, unlike relative mins and relative maxes where you have to look at how the sign changes, from like positive to negative of the first derivative or negative to positive, an inflection point just says, there's a change. I don't care how, there's just a change. I don't care how, there's just a change. And guys, if you notice, this next function is a bit messy as far as the derivatives, and we were talking about how I'm not supposed to be like teaching you derivatives per se in this section. So I'm actually going to go to another page in the last page of notes. Because if you look at the title of this section, it is concavity, and part of we don't want to circle. Part of concavity is, like part of increasing, decreasing was critical numbers, part of concavity is inflection points. They are what we call the zeros and dne's of the second derivative possible, and then if there's an actual sign change, then we call them actual. They're just candidates up here. And they've passed the test if they've made it down here. If you actually see that sign change in the sign chart. However, the second half, it's not really half. Just the last concept for section 3.4 is the second derivative test for relative extrema. Wait, whoa, relative extrema. They only come from critical numbers. We wrote that in our forever card. The only candidates for relative extrema come from critical numbers. And guys, that has not changed. Because, don't you see critical numbers up here at the top again? Right now, your worlds should be colliding just a little bit. Section 3.3 and 3.4 are kind of coming up against each other. Wait, critical numbers are the first derivative. Why is this in the second derivative section? Because we can use the concavity, the curvature at critical numbers, if it exists, to sometimes shortcut or determine relative extrema another way. If we have a horizontal tangent line, if we have a horizontal tangent line, if we have a critical number, a place where the first derivative is 0, and if we plug into the second derivative and see that there's concave upness, concave up nature at that critical point, we can say, guess what? You're a relative min, and I didn't need a sign chart and a before and after to know it. Or if we have a horizontal tangent line, I know, you guys have done a great job, and the second derivative is negative, we can say, we know you're a relative max without knowing the sign chart before and after. And if the test fails, we say, oh well, we have a backup plan, and our backup plan is to go back to a sign chart of a first derivative like homework 19. Alright, kiddos, this is the end of our chapter. We might not have done tons and tons and tons of practice, but work on homework 20 tonight. You have all the key information. Study your forever cards because you have to get these concepts down. Here's what I'm going to do. I am going to move the forever quiz to be back to Thursday. But my rendered people, if you could take it by the end of the day tomorrow, come into my room at any point in time. Your life will be a little bit nicer and more spread out. You can also do it at lunchtime on Thursday. Let's save the forever quiz until Thursday. As you guys notice, you have some forevers to be writing and studying. Sound good? Bye guys, see you later. For the forever quiz, MVT is the only strict memorization one to worry about. Everything else is the concepts. MVT is the only memorization one. All the rest are the